So that's from Polchinski book. And so let's so you have 2 weeks to do that. All right, guys. So let me continue where we ended. Before I'll remind you the starting point for today's lecture, but any questions? All right, so what we did light phone analysis. So what we did, we actually took the light phone gauge. So motion prime, we set it equal to x plus. And then what we did, we choose a particular gauge that L sigma of gamma sigma sigma of the bullshit. The last condition is that we use wild invariance on the bullshit to one. So we showed that this H can always be made locally. So it can always be made locally. So locally because we didn't talk about any topological obstructions whatsoever, and we just did analysis at at the level of differential geometry. Okay, so once we have this gauge, so what we showed, we computed the Lagrangian density, and I'm not going to write it down, but I'm going to write down the Hamiltonian, right? So the Hamiltonian of what I call string. So things is fully formed. L over an integral from 0 to L. And again, remember that what we are discussing right now, we're discussing open strings. So I put a small subscript open. And then I have this sigma 2 pi alpha prime pi. So it takes a very nice quadratic form. Sigma xi, sigma xi. Okay, so that was our Hamiltonian for the open string. Okay, so that's our starting point. So so in general, Hamiltonian is a function of momenta and generalized coordinates. And once we know the Hamiltonian of the system, we can derive the equations of motion. And so the equations of motion take that form. So del Q let me just write down the equations for the string. Okay, so once we have this Hamiltonian, the equation of motion will take this form. I have delta of x minus. Remember that x minus is a function of tau only, and the rest guys, pi, are functions of tau and sigma, and the same with xi. So del tau of x minus is del h over del t minus. So our independent variables are x minus and correspondingly p plus conjugate and conjugate momentum densities and x of i's. Okay, so this guy equals, right? So we have to recall relation between p minus in the light phone gauge and the p plus. So this is the same as del minus del H over del P plus. And so you can see that the only place that P plus enters, it enters here as an overall factor. So this becomes H divided by P plus. Okay. So that's the first, that's the equation of motion for X. Then we can derive the equation of motion for P plus, it's a conjugate variable. So basically it's the same as minus del tau of P minus, which is del H over del X minus. So if you look at our Hamiltonian, you can see that it doesn't depend on X minus, which tells us that this guy is 0. And so from here we conclude that P plus is conserved. Is conserved quantity. Actually, up to a sign is related to a P minus, which is like on Hamiltonian. Okay. So, and the remaining equations of motion take this form. So I have del tau of xi. Now there I could just take simple derivatives because our generalized coordinates and momenta depended only on tau, didn't depend on sigma. So those guys, x sub I, they depend also on sigma coordinates. So what I have to do, I have to take a variational derivative, right? So this is a slight generalization of equations of motion. So delta sub I, and then I have del tau of P sub I equals minus variation over delta x sub I. Okay, so those are the remaining equations of motion. And so let's just derive them. So here I have a Hamiltonian. I take a derivative with respect to P sub I. So there are two P sub I's. So I will have let me write it down in this way. By alpha times C times P sub I. Okay. And so what I did, I actually introduce a parameter C. The meaning of it will be clear in a second, which is L over 2 pi alpha prime P plus. Okay, so up to a factor of 2, that's a prefactor in front of the Hamiltonian. So what we see is this guy, C over 2. And so you can see that the factor that is 1/2, it will be cancelled by variation of P sub I. And so we are left 2 pi alpha prime C P sub I. Okay? And so here we just have to take a derivative with respect to x sub I. So when we take this functional derivative, we actually have to integrate by parts. So there will be an additional minus sign. And so it will be C over 2, 1 over 2 pi alpha pi times a factor of 2. So there is a minus sign in front, and then there is del 2 sigma of x sub I. So this is a minus sign that comes from differentiating by parts, and then there is a minus sign in front of it. And so our equation of motion takes form. So it's C over 2 pi alpha prime del sigma x sub I. All right, so very good. So we derive the equations of motion, and so you can see that this is the equations of motion describing. So what we have E minus 2 free fields. Right? So our free fields are x sub I and corresponding momenta P sub I. d minus 2, because remember the index I goes from 2 to d minus 1. We use one of the spatial coordinates to make up the Lycombe. Okay, so now we can derive the equation of motion for the x variable, right? So the way we do that, we'll just differentiate this guy by tau. So I have delta tau of x of I equals 2 pi alpha prime c times delta tau x of I. And I can use the equation of motion for the momenta, right? So use EOM here. So that will lead to 2 pi alpha prime times c over 2 pi alpha prime delta sigma of x of I. Okay, so you can see the 2 pi alpha prime nicely cancel, and you can see the meaning. Of c squared, the parameters that we introduced, because what we have here a wave equation, right? So that's a wave equation, and c is the speed of sound, the speed of propagation of our waves. Okay? So this is wave equation. C. Okay, so what we have to do next, we have to go ahead and solve this equation, right? We have to do this subject to appropriate boundary conditions. So remember that the only Lorentz invariant boundary condition for open string were Neumann boundary condition. Neumann boundary condition. And so in the Lycombe gauge, that translates into a requirement that del sigma of x of I, and sigma equals to 0, del sigma of x of I, when sigma equals to L, so it must vanish. Okay, so I'm not going to go ahead and solve the wave equation. I'm sure you've seen this in your undergraduate course before. So I'm just going to write down the solution. Okay, so we must have a Neumann boundary condition. And so I can just go into a Fourier space and solve it. And so the answer takes the following form. So I have x of I tau sigma equals x of I as a function of tau, it's just a constant, sorry, plus g sub I over q plus tau. And then I have plus I alpha prime, okay, and an infinite sum, n equals minus infinity plus infinity, n is not equal to 0. So what I did, I actually isolated the 0 mode. So this is 0 mode, right? So when we do the Fourier mode expansion of our wave equation, right? So our function must vanish at both ends, so we expand in terms of cosines, right? So our harmonics are cosines, and cosine expansion has a 0 mode, so that's going to be our 0 mode. And then I have a summation of all harmonics except for 0 mode 1, 1 over n, alpha n I, e to the minus pi I n c tau over L times cosine I and sigma over L. So you can see that cosine pi sigma n over L are complete set of functions that satisfy Neumann boundary condition at the end. And the tau dependence is dictated once you solve that wave equation. Okay. So what I did here, I introduced those two parameters in my mode expansion. So we'll talk about them in a second. But what I want to discuss now is simple reality condition. Okay? So we are looking for a real solution to this wave equation. So what we require is that xi of tau sigma conjugate equals xi tau sigma. And so that will put a constraint, and so the constraints are alpha sub n I complex conjugate equals alpha minus n I. Okay, so this is just a reality condition. So this is just a reality condition. Okay, and once we go in a little bit and do our canonical quantization, so this reality condition will translate into a hermeticity condition so our amplitudes of the Fourier mode will become operators, and so the reality condition on the coefficients will turn into a hermeticity condition of the corresponding operators. And so what we will end up having once we quantize is Hermitian conjugate of that equals alpha minus n I. Okay. So that's when we do our quantization. So now I told you that I introduced in the zero mode, I split zero mode into two plots. So there is p sub I that I introduced there and x sub I. So what are the meaning? What is the meaning of those parameters? Well, so what we can do, so you can see explicitly that x sub I is equal, by definition, is 1 over L integral from 0 to L d sigma x sub I of tau and sigma. So I have the expansion, and so when I integrate over the whole interval, all the cosines will disappear, and so I will get x sub I, which is a center of mass coordinate. Center of mass. Well, actually, I'm a little bit sloppy here, so I will get just a center of mass motion of the string. Right? So this is center of mass. Okay. Now, what is the meaning? What is the meaning of p sub I? Well, so if we are asked the question, what is a momentum? This is a momentum in a space-time, right? So p sub I is the momentum of the string. Momentum of the string. So what I have to do, so I just have to integrate momentum density over the length of the string. I have d sigma of p sub I of tau and sigma. Okay, and so this equals from 0 to L d sigma. So if we look at our Hamilton-Jacobi equation, so you can see, we still have it somewhere. Yeah. So you can see that p sub I is del tau of x sub I, and so for some reason I choose to write it down again as p plus over L. So I just substituted the value of p, and then I have del tau of x sub I of tau and sigma. Right. So. Yeah, so at least you can see that it's proportional from this relation delta out to x of I, and the coefficient of proportionality will be P plus over L. So I have a Fourier mode expansion. I will take a derivative with respect to tau, and then integrate over the length of the string. So all non-zero mode contribution will vanish, and so the only piece we will have left will be a contribution from a term linear in tau. So that's going to be equal P sub I over P plus times the length of the string. And so you can see that momentum, maybe I should put a hat here. So the parameter P sub I that we introduced in our zero mode solution of wave equation has to be identified with momentum of the string in transverse coordinates in our Lighthof gauge. Okay. Okay, so any questions? So this is a central, so what I meant there is actually a central mass position of the string. So I integrate with respect to sigma variable. So I will get a trajectory of center of mass of the string moving with a given space momentum P sub I. Okay. All right, guys. So any questions so far? Yes.
Just confused about the tau dependence of things. So x sub I is dependent on tau, right?
Yep.
The P sub I, is it constant or is that also a function?
P sub I. So in general, there is a tau dependence, right? But the tau dependence will come only from the non-zero modes, right?
Okay.
So it's when you solve the wave equations, the tau dependence is completely fixed on you, right? So so the tau dependence require so you can see it. So this is a zero mode, right? So all those guys cannot depend on sigma, right? Because I have to satisfy this boundary condition. Now, when the derivative will vanish, so if you look at the wave equation and del sigma x I vanish, then your equation for the zero mode become del 2 tau xi equals to 0. So the general solution of that equation is you have a constant plus some other constant times tau. Okay.
Okay, but that's not really a constant.
No, this one is a constant. That's why. Okay, so
it's a constant function.
No, this guy is a constant. I'm saying that when I take a coordinate xi as a function of tau and sigma, and I integrate over the length of the string, that will give me the motion. That will give me the motion of the center of mass of the string. And so you can see what will happen. So if I do that, then I will get right? So this is my x of I plus the integral we computed right now. So it's going to be times L plus P sub I times L times tau and 1 over F, right? So it's just x of I plus P sub I times tau. So what you simply get the equation of motion of the central mass of the string.
Okay. So this xi here is static.
I don't know. Let's put it a little bit here. Okay, so that's a center of mass coordinate of the string. And of course, it will depend on tau. Now, to answer your question about P sub I, in principle, in general, it will depend. So there is a tau dependence. But what happens is that using Hamilton-Jacobi equations is proportional to del tau of x sub I, and we still have to integrate over the length of the string. So because we would have had a specific tau dependence from these modes, but those will not contribute because we have to integrate cosine over half or over a period, right? So it will vanish. So the only contribution will come from the zero mode. And the contribution from the zero mode is tau independent. Because the zero mode depends on tau only linear. Right? Okay. Very good. Okay, so without any questions. So again, everything is very straightforward, and this is some of the exercises that you would be doing in your homework. So you will end up recalling everything you knew about wave equations, okay? And I could give you some lecture notes that I was teaching on, but it's undergraduate material. I'm sure you have it. Good. So we're done with that. And right, so I'm not going to write down the explicit formula for P sub I, right? I'm going to use it, but it's given by this relation, and so you can just solve it. Okay, so now what we want to do, we want actually to quantize the system, and so we have to promote our Poisson brackets that come up in this Hamiltonian framework into canonical commutation relations. So let me write it down. So all we are doing, okay, yeah. So we go into canonical quantization. Okay, and so what we have to do, we have to say that there is a bracket between conjugate momenta and coordinates, and so that's in case we have a non-trivial space-time metric. So this eta minus plus is going to be equal to minus I, and then so x sub I and p sub I becomes operators, so they also satisfy a commutation relation. So I have x sub I, p sub j. So one is a function of sigma, the other one is a function of sigma prime. And so this is I, delta ij, right? And now I will have additional delta function, right? Because I have fields rather than well, I have, if you wish, momenta and coordinates which are densities. It would be additional delta function. Sigma prime. Okay. So that's a canonical quantization. So we identified coordinates, momenta, and so we have to impose these commutation relations. Now, what we want to do, we want to understand how that commutation relation translates on the coefficients of our Fourier mode expansion. Right? So those are these guys, and those coefficients. And so I'm not going to do it in general, but the way to do this is the following. So what you have to do, so you have a Fourier mode expansion. What you have to do is plug in the Fourier mode expansion for x sub I, a Fourier mode expansion for p sub j, and you have to do a Fourier mode expansion for the delta function. So that's a very nice exercise. I'm not going to do it on the blackboard because first I will get lost in various numbers, but I'll just illustrate it for the central of mass, right? That we will get the right commutation relation to the central of mass position. So let's look at this. So this combination will contain, so gives a commutation relation relations for zero mode coefficients. Plus higher harmonics, right? Plus higher harmonics. Okay, what I'm going to do, I'm just going to look at the commutation relation for the zero mode. So the x sub I, well, okay, so when I was writing down this commutation relation, those are the only non-trivial commutation relations. So all the remaining ones, for example, x sub I of sigma, x sub j of sigma prime equals to 0. So all other commutation relations will vanish. So those are the only one non-trivial. So let's look at this one, and out of this bracket, let's pull zero Fourier mode. So x sub I as a function of, well, of course, there is an implicit. So in the zero mode here, I will just have x sub I, and then I have to commute it. I have to commute it with p sub j, and p sub j we computed there, so it's going to be equal p plus divided by L times p sub I over p plus L, and so this should be equal. I have to put j, right? So this should be equal. What I'm doing, I'm just checking that it will, at least for the center of mass, you will get the commutation relations that you are familiar with. I guess I have to put so I delta ij, and so the zero mode of the delta function is just 1. Okay, so what we see that out of an infinite set of Fourier harmonics, so this is for the zero mode, right? So again, you do that and you isolate tau dependence, and you pick up different tau dependencies. So what you'll find out here, so you can see that everything cancels, and you're back to a familiar commutation relation. Okay? So this is a commutation relation for a point particle. For a point particle. With central of mass coordinate x sub I and momentum p sub j. Okay, so I did it only for zero modes, but you can repeat everything, including these high harmonics, and what you will find out that this canonical commutation relation implies the following identity on the Fourier mode. So I have alpha m I and alpha j m equal m delta I j delta m minus m. So this is m is not equal. So. Good. Well, so if you look at this algebra, so the first commutation relation is very familiar, it's the central mass motion. And this one should remind us the simple harmonic oscillator algebra. So this is simple harmonic algebra in disguise, and we can make it very explicitly. So what we can do is the following. So we can fix m. And once we fix m, so you can see that different values of m, so we have this algebra naturally breaks into is a direct product of various subalgebras involving m and minus m, right, for different values of m. So what I can do, I can study this oscillator algebra, shows that it is an oscillator algebra by fixing M first. So what I can do, I can do this simple rescaling, square root of M, and I denote this as A. And I have I minus M, that's the other generating the algebra. So I'm going to call this a dagger. So I put a dagger here because those two operators, remember there was a reality condition, and that reality condition translated into a hermeticity condition on corresponding coefficients. That's why if I declare this to be A, I have to say that whatever I have there is a Hermitian conjugate of that. And so now you can see that the algebra, once I did this rescaling, so the algebra takes this very simple form. So, well, actually, I have to fix M and I, right? So in other words, we have an infinite set of oscillators, right? What we have to conclude is a Polyakov string is, has all the properties of the point particle, right? Center of mass motion, and then it has infinite set of harmonic oscillators. So those harmonic oscillators are labeled by our index M. So M goes 1 to infinity. And then on top of that, there is a transverse index I. Okay? And so we have to recall that I goes from 2 to d minus 1. What's important for us that for each fixed value M, there are exactly d minus 2 oscillators. Okay, so now once we understood how do we quantize the string, we can construct this again following from what we know about a simple harmonic oscillator. We can construct a Hilbert space. Okay. So let's talk about that. So Hilbert space. Hilbert space of a single string states. So what is a Hilbert space? Well, so we have to figure out how do we label our space. Well, first of all, we have central of mass motion. So what I can do, I can label the states as I would have labeled my point particle. Right? So this is same as point particle labels. So those k plus and k minus, those are just eigenvalues, k plus, ki, so they are eigenvalues of p plus and p sub I. So those are our momenta. So in specifically, so p plus of k plus ki is going to be equal to k plus I, and the same for p sub I. Sorry, yeah, p sub I plus p sub I. Okay, and so that's our, if you wish, ground state. So think of this as ground state of a string. And that would be the case. So I'm going to now denote, just use a simplified notation, I'm going to call this K without any index. And so that would be a ground state if it is being annihilated by all oscillator annihilation operators by all A's. So what we want, so I'm now introduce additional index, index A, so index which is 0 here, meaning that it is a ground state, which refers to internal excitations of the string. And so it will be a ground state. I'm defining this exactly the way how I would define a ground state for a simple harmonic oscillator, except that now I have lots of simple harmonic oscillators. So I have to impose this condition. And so this is correct when n equals 1 and so on. Well, let me write it down that n is positive, right? Remember that for the positive values of m identified with annihilation and a negative with creation operator, and then the index I you get from 2 to d minus 1. So that's our ground state, and so you can see now that, well, we can normalize this ground state. So I'm just going to be, so there will be, of course, because momentum is a continuous, there will be a delta function, but I'm talking about normalization here. So I'm going to normalize this to 1. Okay? And so in general, so I can construct general excited state of the string. And so what I have to do is exactly the same how I construct excited states of simple harmonic oscillator. I'll just have to act with raising operators. Right? So I will call it n, and then there is k here. So, so what I can do, I can act with operator alpha sub n, alpha sub I minus n. Right? So little n are positive. And so I can act with this n comma capital N I comma n times, right? So this would be the analog of this would be that I'm acting with a plus n times, right? And on my ground state of the harmonic oscillator, right? So right, so the thing is that we need to do the right normalization. So that would be normalization of the excited state for harmonic oscillator. So in this case, over here, this is the pass, so here what I will have a slightly more complicated normalization. You can figure it out. This is n factorial 1/2, so this ends. And then here I can construct an excited state by acting with any raising operator. So n goes from 1 to infinity, and then I can act with any transverse oscillator. Okay, so this n, again, n are occupation numbers. Occupation numbers of I comma n. Well, the only The only difficulty if you would here compared to a harmonic oscillator is that you have to keep track of this infinite set in this, but otherwise, very easy. All right, guys. So very good. So now I want to make one small comment. So what we did so far, we constructed a Hilbert space or a single string, but and that's okay as long as remember that now you can see that string theory can be quite complicated. So first of all, the string has internal excitation itself, right? So there are those ripples, those waves, they move along the string, so those waves can interact. So that's one type of interaction, and that will occur for every string. So if I have a single string, then there are these running ripples, and in principle they will interact. They don't interact in our case because the theory of these ripples is just a set of simple harmonic oscillators, right? And so what we did when we constructed this Hilbert space, we constructed a Hilbert space for the internal excitation of a single string. So now if you ask me what is the Hilbert space of the string theory, okay, so now I have to say, well, so first there are excitations in a string, but then the strings themselves can interact, so the string can join and split. So I have to take into account that there are states that belong to the other string. So in fact, the full Hilbert space of the string theory, if I turn off all the interactions, and that's typically how we build up Hilbert spaces in quantum field theory. We'll turn off the interaction, we'll find out what the Hilbert space looks like. So you can see that it's actually a Hilbert space of no string at all, and then there is a one string Hilbert space. So this is what we just discussed. And then there is, so it's a direct sum, and then there is a Hilbert space of two strings and so on. Now, the Hilbert space of the n strings, as long as the strings are not interacting, all I have to do, I just have to take a product of single string Hilbert spaces. So it will be a Hilbert space of a single string raised to the nth power. Okay, very good. So now, what we do, you know how does the string theory look like in the limit when there are no interactions between the ripples on the string and when the strings cannot join or split. All right, guys, so very good. So let's move on. So, yeah.
For particles, for quantum field theory, when we do such a Fock space,
Yeah.
Maybe before the spin theory particle, we need to synchronize.
Right. So
But here we have no spin static.
right. So actually, the title of the course is bosonic string. So does that answer your question? So it's a very good question. I just admitted this. So what happens is you're absolutely right. So when we talk about multi-string configuration space, and we build up wave functions, we have to know whether we symmetrize or anti-symmetrize it, and that depends on the space-time spin, right? So the way to do this is to construct the generators of Lorentz transformations. Okay, so we can do. It's a little bit more difficult to do in a light cone gauge, but it can be done. And so once you do that, you can ask the question: what is the space-time? What is the space-time spin of my single string excitation? And that's where the word bosonic comes from, because you will find out that all these excitations of the string are actually integer spin excitations. And so just to be more precise here, what I mean, because they are bosonic excitations, I actually have to talk about a symmetric product, single string Hilbert spaces. Okay, that's a good question. All right, guys. So let's move on. So any other questions? So now we are proceeding exactly the same way. How you would do with say harmonic oscillators? So we have mode expansion. We constructed our oscillator algebra. So what we can do now, we have an explicit mode expansion for x sub I and p sub x sub I is a function of tau and sigma. Whenever I can construct p sub j as a function of tau and sigma. So remember that our Hamiltonian was an integral over the length of the string of x sub I and p sub I. So I can substitute the mode expansion and integrate over the string. You can do it yourself. And so I'm just going to write down the answer what you will get. So we will find out that the Hamiltonian of the string in a Fourier, once I express it in terms of this Fourier coefficient, so we'll take the form plus 1, 2 plus alpha prime. So here I have some I equals 1 to infinity, and I have alpha minus ni, alpha ni. Okay, and so there, what I mean by I is that there is an implicit summation. Summation over I. Okay, so that's what our Hamiltonian would look like. Now, once we do our canonical quantization, what will happen is that we actually have to care. So p's commute between themselves, but alphas do not commute, right? So they satisfy a simple harmonic oscillator algebra, and so the order here matters. And so once those coefficients become an operator, they can be an ordering constant. And so let's call this ordering constant A. And so this is purely quantum effect, right? So this is a quantum effect. So this possible constant arises because there is an ambiguity. How do I order my raising and lowering operators? So far everything that we did, depends on two parameters, right? So the two parameters, two numbers that enter the theory are D, the number of space-time dimensions, and A. So those are three parameters. Well, they are not a free parameter, but they are not determined. And so what we're going to discuss right now, we're going to actually figure out what are the value of this of these two numbers. And so what we will find out is that E equals 26, which is a very stunning result. It tells that this theory is consistent only in 26 dimensions, this theory of simple non-interacting strings. And moreover, we will predict a very specific value for A. And so this value of A is going to be equal to -1, so it's not 0. So that's what we are in right now. So the purpose of discussion I'm going to have right now, it will not be very rigorous. I'll give you, but tell me if you're not convinced, okay? I keep saying that it's not rigorous, but it looks very convincing to me. So I'll give you a not very, I'll tell you what would be the rigorous argument when we would do the light cone gauge. Well, when we do analysis in a light cone gauge the way we're doing now, but then we will rigorously rederive these numbers later when we do covariant quantization. So, so where does those numbers come from, and what determines those numbers? So what happens is that, remember, our guiding principle in building this theory was Lorentz invariance. And so what we're going to show now is that if we want Lorentz invariance to be preserved after we quantize the strain, it will fix the values of DNA. Lorentz invariance will fix Lorentz invariance in d dimensions, right? So we're talking about Lorentz invariance in the space-time with string propagates. So Lorentz invariance in d dimensions will uniquely fix these two numbers, DNA. Okay, so I'm going to give you an argument for that, but before I'm going to give you the way to proceed, and you can look at original papers. So the idea is that all the computations we done was in a light cone gauge. And because, so in the light cone gauge, we said explicitly what is our time, so we broke Lorentz invariance. And so we have to check what are the conditions that our operators, so in particular, so we can construct a Lorentz rotation operator, and then we constructed a space-time momentum, right? So the space-time momentum entered in the zero-mode expansion on the string bullshit. And so we can construct these Lorentz generators of Lorentz transformations. Again, express everything in terms of creation and manipulation operators. And we know that it satisfies, it must, for Lorentz invariant theory, it satisfies certain commutation relation. So enforcing this commutation relation will fix you DNA. Okay, so that's how we would have done it seriously. You would find out that this commutation relation will be satisfied only when DNA takes the specific values that they hold on the background. That's a very long route, right? Because that would require me to actually construct integer generators in the light cone gauge, figuring out their mode expansion and computing commutation relations and doing all that stuff. That's too difficult. However, I'm going to give you now an argument that doesn't require that, and we will still be able to get the right answer. If you are not happy with that argument, you'll just have to wait one more lecture, and we will do covariant quantization, and we'll derive that rigorously. All right, guys? So let's see why you believe in 26 dimensions. Okay? So the first thing is we have to sort out A. So let's talk about A. So everything that I have taught before, I could have talked about a simple harmonic oscillator. And so in a simple harmonic oscillator, there is still this problem, right? So I could have when I do canonical quantization, I will derive a Hamiltonian, and the Hamiltonian will be h bar omega, and then here I have a data A plus some constant, right? So so how can we fix? So we know There's no 1/2 here. So we know that you could do quantization correctly for a simple harmonic oscillator. So we must have the energy spectrum. This is H omega n plus 1/2, right? Where n. So if I have some state of a simple harmonic oscillator, so n is just the occupation number, A dagger A, after 1/2 n is the little n. And so this is a correct way of how we should have quantized a simple harmonic oscillator. By the way, some people, there were some papers on the archive where what I'm going to discuss right now, people claim is not to be the case. For example, that there is no critical dimension for the string. And the reason, if you go and look into their derivation, so the reason what's happening is that the way they quantize the string leads to an incorrect spectrum for simple harmonic oscillator. So the way how we're going to approach string theory is we're going to require that wherever rules we're using, we're not changing rules just because we're dealing with a string. We are applying exactly the same rules how we do quantum mechanics or quantum fields. And so in particular, going back to the simple harmonic oscillator method, wherever our rules are, it must be such that it produces a correct spectrum of a simple harmonic oscillator. In particular, this number is 1/2, okay, and nothing else. So now we can step here and ask the question. So A dagger and A are operators, right? So I have A comma A dagger commutator equals to 1. So how can I write down the Hamiltonian in such a way, and how can I fix this A in such a way that I get the right energy spectrum? And so the idea that comes from a simple harmonic oscillator that what we have to do, so when we have a product of raising and lowering operators, all I have to do is just to take a symmetric ordering of these operators. So you can, if you use a commutation relation, so you can see that this will translate in h bar omega over 2, and then I have 2 A dagger A plus 1. And so now when you compute the spectrum, you will get precisely the right. Energies of excitations. All right, so we're going to do exactly the same. We're going to do exactly the same for our string, right? So there was an ambiguity there, but we know that all these operators are actually up to a factor, creation and annihilation operators of simple harmonic oscillator. So we're going to use exactly the same ordering prescription as we used up there. So I have the first piece is unambiguous, and then I have plus 1 over 4 p plus alpha prime, right? So there is a factor, additional factor of 2, and then what I'm going to take here, I'm going to take here a symmetric ordering, n equals 1 to infinity, alpha minus n pi, alpha n pi, plus alpha n pi, alpha minus n pi. Okay. Now, we can proceed exactly how we do in harmonic oscillator, pretty much following this step, using the commutation relation, p plus 1 over 4 p plus alpha prime. So here I will have some n equals 1 to infinity. So here, once I commute those guys, I will get 1. Right? So I have alpha. There will be a factor of 2 here. So I will have 1 over 2 alpha minus I alpha n. So I'm having a normal ordering now, right? So much like in a simple harmonic oscillators, all the annihilation operators go first. So I have a normal ordering here, so it's a factor of 2. Now, each of these commutators will give me a factor of 1/2. And now I have to make sure that I take care of this I index, because there are precisely d minus 2. So precisely d minus 2. So it would give me 1/2 if those operators would be correctly normalized, right? So it gives me 1 here, but these operators have an additional square root of n, right? So those guys have an additional square root of n compared to the canonical normalization of oscillator algebra. And so I will have square root of n times square root of n. Okay? So I have this computation. Okay, so now you can see that I can write out the Hamiltonian in this way. P plus alpha prime, 1 over 2 P plus alpha prime. I equals 1, sorry, n equals 1 to infinity, normal ordering here, plus d minus 2 over 12, sum n equals 1 to infinity of n. Right? So whatever we call this ordering constant, so this is our ordering constant A, is d minus 2 over 2 times the sum of all integers from 1 to infinity. Okay, so how do we deal with that sum? So that sum is divergent, and that's what you will hate me for, what I'm going to do. I'm going to do it anyway, and I told you that, so that's if you is the only unsatisfactory piece of derivation. But I promise you in covariant quantization we rigorously derive it. So we're going to do the following trick. So what are the sum of all these numbers? Okay? Sum n equals 1 to infinity of n. Well, I cannot compute that. But what I can compute this, assuming that k is larger than 1, right? So this sum is going to be convergent. And so in fact, there is a name for this sum. So if I have a sum of all integers raised to the power of minus k, so that gives me a data function evaluated at value k. So this is Riemann data function. Okay, so I don't know how to compute that sum, the one there, but I know that this sum is a Riemann data function as a function of k. So that tells me that actually the constant a that I need to is d minus 2 divided by 2, and then what I need to know, the value of Riemann zeta function evaluated at minus 1. So what I implicitly did here is very similar. For example, if I talk about 1 plus x, so it's 1 plus x squared plus x cubed and so on, 1 minus x. So there is a series expansion. That series expansion converges provided x is less than 1. But I know that this series sums up to some function, and I can determine the value of this series outside the radius of convergence if I do analytical continuation of the function. So what we have done here, so we know that the Riemann zeta function sums all integers, provided that k lies within certain radius of convergence around infinity. So k must be very large positive number. But what I can do then, I can do analytical continuation. So what we did here, analytical continuation of the Riemann zeta function around its expansion about infinity, right? So this is you can think of this as an analog of a Taylor series expansion of the Riemann zeta function for large values of k. Okay, and then I did an analytic continuation for small values, and the point is that this analytic continuation is unambiguous. Okay, so sometimes when you have branch cards, you can get different answers as you do analytic continuation depending how you approach. So this is not the case here. It takes a very nice value. So actually, it's minus 1 part. Okay. So now, if somebody asks you, if you guys would be right? 1 plus 2 plus 3 equals to minus 1 part. That's the right answer. Okay, very good. So, so we are on our way. So we determine the value of A. Again, it doesn't fix us D, but it tells us that A must be related to D. So that's very nice. So now what we need to do, we will do the following. So again, the key point in fixing D is Lorentz invariance. So we know what will be and we are in a light cone, so Lorentz invariance is not guaranteed, right? So the quantization must break the Lorentz invariance. So the requirement we're going to make now is that the spectrum of string excitations is Lorentz invariant. Okay, so that's a requirement that we're gonna have, and let's see where it leads us. Well, first of all, we need to compute a spectrum, so we need to know. So again, what the string looks like. So the string looks like a point particle, and then it has its internal excitations. So from the point of view of center of mass motion, internal excitations of the string are just particles of different mass. So let me write it down here. And so you can see actually when people talk about string theory as a candidate of a unified theory, you can see this unification happening here. So internal excitation of the string correspond to different masses, actually, and spins. So, so if you were to compute the spin of those internal excitations, it will be different. It will be integer, but it will be different space type spin. So different masses and spins of center of mass motion. Right? So in some sense, a single moving string represents an infinite set of particles of different masses. So I keep talking masses, so exactly what are the masses, how do we compute it? Well, so recall that in a light cone gauge, P minus is a Hamiltonian of the system. And also, so the m squared for a point particle is just 2p plus p minus pi, right? So this is just a point particle particle spectrum in light cone gauge. So this is just 2p plus, right, times Hamiltonian minus pi times pi. Okay. So we know what the Hamiltonian of our string is. It's given on the blackboard. Right? So let me erase this. And so you can see actually from the perspective of the center of mass motion, what is the spectrum of the string excitation, right? So in other words, what I'm doing here, I'm subtracting from the light cone energy, I'm subtracting just the kinetic energy of the string. And so if you wish going into the center of mass frame, and so what I will be measuring there is exactly m squared. So you can see that m squared, so I take the Hamiltonian given by that expression there. So m squared you have to think as an operator that acts on the Fock space of single string states. So I times 2p plus minus pi to cancel. And so I have 1 over alpha prime, 1 over alpha prime, and then I have here m plus 2 minus d divided by 24, where this n is a total level of string excitations, right? So I have to sum over all transverse oscillators, right? And I have to sum over all oscillators. And then there is n times n sub I n. Right? So for a simple harmonic oscillator, so this guy is just eigenvalue alpha minus n alpha. Okay. So again, this would be just the occupation number of harmonic oscillators. There is additional factor of n because of our commutation relations. All right, guys. So very good. So what do we conclude? Okay, so now we have a spectrum, and you can see that low-side integers. So we can predict. So yeah. So n is positive. So we can predict the spectrum of a string. Right? So let's look at the lowest excited level of the string. So ground state. Okay. So the ground state of the string, so we are not exciting anything, and so you can see that m squared. Okay. I will put 0 here. So m squared 0 is just going to be equal to 1 over alpha prime 2 minus d over 24. Okay. Now, you can see our problem, and if you are pessimistic, that's where you stop learning string theory. You see that there is this m squared, and we know that it's related to d in this way, and I promised you that that's the right formula. We'll derive it. The only subtlety was this analytical continuation of the zeta function. But you can see that m squared 0 is negative if d is larger than 2. So what this tells you is that the theory is safe. For one thing, for sure, one of the things that we know about the theory of world that we live in more than 2 dimensions. And that tells us that the excitations of the string are actually tachyonic. So the way to think of this, so that corresponds to, so this is analog of a quantum field theory. So I can think of a scalar field, and my Lagrangian is -1/2 del phi squared. And then in general, I have a potential, E of phi. And so in order for my quantum field theory to make sense, E of phi that would be bounded better be bounded from below, right? Because otherwise, if it's unbounded, then I can never construct a bound state. I can never construct a normalized wave functions. So my Hilbert space will not contain that. Well, there will be no normalized excitations. So what happens here is that this thing. So if I do an expansion around small fields, or look at the free scalar field, then the first term is m squared, phi squared divided by 2. And so you can see that when we have positive masses, this potential is very nice. It's bounded from below. However, when m squared is negative, it's not bounded. And so the theory is sick. The theory has that. So what we have here is an tachyon. Okay? And so, so the problem with the tachyon, again, it leads to unstable vacuum. There is simply no vacuum to talk about. The vacuum must be a normalizable state in this theory, and there is no normalizable state. So everything that we continue from here, we have to live with this tachyon. Okay? So the one of the in old days, one of the problems of string theory was this tachyon, and it only was the invention of supersymmetry. People showed, and you will see later today how introducing some additional symmetry provides projection of some states. So some of the states in the spectrum are not physical states. We will see this later. So what will happen is that once you introduce supersymmetry into a string theory, the supersymmetry will provide second projection in the spectrum, and it will remove that. Okay. And again, as you will see in an analogous, well, not analogous, but kind of morally speaking, similar example, that it doesn't change anything else. So it simply projects some states, which means that everything that you will learn about the bosonic string will still be valid in superstring. The only thing is that you don't have to deal with this problem. So, so that was the ground state, and it was sick, but let's continue. So we figured out that if we impose supersymmetry, things will get better. And so, so let's look. Let's look at the first excited level. So first level of the string. So we're looking at the Lycus excitation of the string. Okay, and so you can see that I can get the smallest mass. I can get the smallest mass if n equals to 1. Okay, and then I have to act with a single oscillator. So n 1 comma I must be equal to 1 as well. So I act with a single oscillator of level 1. But notice that the index I is free. I am free to act with any oscillator I want. And so, so in this case, the level 1 m squared equals to 1 over alpha prime, and then I have 1 plus 2 minus d divided by 24. So 1 over alpha prime, 26 minus d divided by 24. So, so now it's a point to talk about Lorentz invariance. Right. So, so here at level 1 we have a single state. So we have a tachyon as a degeneracy. So degeneracy equals to 1. So it was a single state. Because it is a single state, it's a singlet under Lorentz transformations, and so there is no problem. If the theory is Lorentz invariant, the massive spectrum of the theory must form a representation of the Lorentz group. So let me write it down here. And that's going to be our guiding principle. For Lorentz invariant theory spectrum of excitations must form a representation of S of D minus 1, 1, right? So it must form, it must be in a faithful representation of a Lorentz group. So at level 1, we don't have any constraint because it's a singlet state. So if it is a singlet state, yeah, sure, it will be a singlet under Lorentz transformations. So no constraints from 0 level, right? And that's because the degeneracy of the ground state is 1, and it was a singlet. So in this case, the first level, level 1. So we know that the mass is up there, but what I pointed out here is that we can achieve this excitation by acting with any oscillator. So what this tells us that degeneracy equals to d minus 2, right? So there will be precisely d minus 2 states, of the string at the first excited level. And so then we have to require, what we will do, we require that there is a representation of SO d minus 1, 1 with dimension. So there is a representation. Let me call this representation R. So there is some representation of this Lorentz algebra in such a way that dimension of this representation must be equal to d minus 2. Okay, so if that is the case, then the first level of the string will simply be in this representation of the Lorentz algebra. So let's talk a little bit about representation theory of Lorentz algebra. Well, so let's talk. The simplest way is to think about point particles. So let's talk about point particles. Point particles in Lorentz invariant theory. Well, so the particle can be massless. So it can be massless, or it can be massive. And so let's see how many states. Well, so first of all, the particle can be in a singlet representation, and that's not interesting. So let's go to a more interesting representation. Well, so if I have a massive particle, I can go to a rest frame. So we can go to a rest frame. And so in the rest frame, the momentum of the particle will simply be m, and then I have 0. So there will be d minus 1 unbroken generators of Lorentz group. And so in this rest frame, the particle must be in S of d minus 1 representation. And so the lowest representation here is the vector representation, and the dimension of the vector representation here. Dimension of the vector representation is d minus 1. Okay? And of course, you can construct a more complicated states. They will be in a high dimensional representation of your Lorentz algebra. But the important point is that whatever, or if you wish, how many states your particle can have, the number of states, the degeneracy of the spectrum of the particle will always coincide with the dimension of well, if the particle is an irreducible representation, will be with the dimension of irreducible representation. Okay, is that clear? So now we can do the same in a massless particle. Well, if we have a massless particle, we cannot go to a rest frame, right? But we kind of can go into analog of a Lightcon cage, Lightcon frame. So that's the frame that we go. And so what we still have left. So we broke S of d minus 1, comma 1. S of d minus 1, comma 1. So in this frame, which we can always choose for a massless particle, the Lorentz group is broken into S of d minus 2. And so by the same arguments as there, whatever the degeneracy of states must be, that it must be in the representation of this little group, S of d minus 2. So in particular, the dimension of the vector representation here, vector representation of the little group, is going to be equal to d minus 2. So now, what you notice immediately, that look, so we talk about the first level of our string, and we found that at the first level of the string, there are d minus 2 excitations, okay? And so they must be in a vector representation, and moreover, we immediately have to conclude that in order for theory to be Lorentz invariant, those states must be massless. Because if they are massive, you just don't have enough states. You should have had at the first level d minus 1 state if they would be massive. So, so the conclusion is that because at level 1 we have d minus 2 states. So that immediately implies that the mass of those states must be 0. Okay, so those states must be massless. Otherwise, there is a different little group that characterize representation. So what we computed the mass there, 1 over alpha prime, 26 minus d, and it must be equal to 0. And so you see that indeed, if we impose the condition that our states preserve Lorentz invariance, the space-time dimension must be 26. So what I did so far, I looked only at the first level, but you can go and look at the second level when you act with different kinds of oscillators. So in that case, in general, you will get not, so here I get an irreducible representation. You will in general get reducible representation. But you can see again, even at the higher level, the requirement that whatever the degeneracies you will get will come up from the sum of irreducible representations, either of this guy or of that guy. It will again force you to choose the same value of d. Okay. So any questions? Yes.
For example, in the 4-dimensional time,
yeah.
the massless particles
Hold on.
always have 2d.
Yeah, so SO2 is the same as U1, right? So there are two helicity states, right?
Oh, so but for general dimension, the dimension of the rotation.
Yeah, the way to think of this is that, so what I did, I went into specific frame. I always can choose this frame if my particle is massless. So if I am sitting in this frame, then I broke the Lorentz invariance into S of d minus 2. So whatever the extra space-time index I have, it must transform in the representation of the unbroken symmetry group, right? So this is the unbroken symmetry group in this frame. So it's like an analog of the rest frame here. So if I take a massive spin J particle, right? So it can be moving, but I can go to a rest frame. So in that rest frame, I will have 2J plus 1 states, right? So if I have spin 1, which analog of a vector representation, I will have 3 states, right? So I start with D equal 4, SO3 vector representation is 3-dimensional. So it's in a vector representation. More questions? No. All right, guys. So we are done with critical dimension. Good. So let's go ahead. So we discussed only open strings. Now I'm going to talk about closed strings. And by the way, so what we found with you in open string is that there is excitation that we can identify with a massless vector. The reason why it is a massless, well, first of all, it is massless at level 1. It's a vector because it has d minus 2 states, which is the right number of states to be carried by a vector. And the point is that once you turn on interactions between strings, so this massless vector field will give you gauge invariance. Okay, so whenever you have an interacting series of massless vectors, that there is an associated gauge invariance. So you can see that somehow open strings are associated with vector fields. Okay? And in fact, so far you can see that this vector field must be an abelian vector field, right? So it's a U1 field, and the reason why it is U1 because there is no in the discussions that we are having right now, there is no freedom to attach non-abelian indices, but in fact, if you read the, I'm not sure we'll have time to discuss this in the course, but there is a way of modifying open string in such a way that this vector field will carry non-abelian indices as well. And so when you study the theory of interacting non-abelian massless vector fields, you will naturally get the Fourier-Mills theory, which is a highly non-trivial statement if you think. So you study the interactions on the strings, and you will find out all the necessary interactions of non-abelian gauge bosons. Well, there is a tricritical and quadratic coupling there, and there is a right vector there. So all will come up naturally. All right, guys. So let's do the following. So let me start a little bit, 5 minutes, and then we'll take a break. Okay, so now so we're done with open string, and now we go to closed strings. So now we go to closed strings, and so we're going to repeat exactly the same steps. We're going to repeat exactly the same steps here. So we're going to choose fix a Lycombe gauge. So again, x plus is going to be tau. Then I have del sigma of gamma. Sigma equals to 0. And then I have gamma equals to -1. So everything is same as before, except that there is there is an unfixed symmetry. Okay, and this is a very important symmetry. So without that symmetry, we will not get a graviton. But it's really, if you think, I just enjoy it so much how these things like a graviton shows up by being careful about something. So something that we have to be careful, what this gauge doesn't fix is that there is a symmetry. So we have, remember that we have a closed string now, right? So what this tells us that this sigma coordinate is identified with the length of the string, right? And so because the string is closed, there is no beginning and there is no end of the string. And so what this tells us, that tells us that there is a symmetry when sigma goes to sigma prime, which is sigma plus an arbitrary function of tau. Okay, so in other words, there is a symmetry associated with where do I choose the origin on a closed string. And that will be crucial in order to derive the right graviton. So for now, this is leftover symmetry. Leftover symmetry. And we will deal with it. We will figure out exactly what are the consequences of this symmetry on the spectrum when we determine the spectrum. And so now all I have to do is that the analysis will go as before. So let me just write down these formulas and we will have the break. So, again, I'm going to write down open and closed strings so that I can contrast. See? So in case of open strings, so we have the mode expansion of tau and sigma, which is xi plus pi over p plus tau and plus I, so alpha I 1 half, so and plus 3 and 0. Again, alpha I. Now, plus I and sigma divided by L. Okay, so that's what we had in the case of open string. Now we have closed strings. And so again, we have this mode expansion for the closed strings. So the mode expansion will take the following form. So again, there is a zero mode, and you'll zero mode associated with center of mass motion, and so it must be exactly the same as in all strings. And so again, you will end up solving exactly the same wave equation, except that there would be a different boundary condition. So the boundary condition here would be xi of tau sigma plus L must be equal to xi tau sigma. Okay. So you have a periodic boundary condition. And so if you solve the wave equation, so instead of a single set of oscillators, right, a single set of harmonic modes, which were cosines, so here there would be two sets. And I'm using a slightly different memorization here. Alpha I over n. And then here I have e to the 2 pi I n, so sigma minus c tau divided by L. Then I have plus alpha and tilde I divided by n e to the minus 2 pi I n over L sigma plus c tau. Right, so you can explicitly see that it's actually a periodic. So let's do that upstairs. Okay. So you can believe me that, well, to the same level as I did open string, I never solved that wave equation, so I'm not going to solve this one either. Very good. So let's have a 10-minute break, and after the break, we will start with this.